Welcome to the solutions to the circular motion and gravity free response packet. Let's go ahead and jump in here with 2010 Form B, question that year. A small block of mass 0.15 kilograms is placed at point A at a height of 2 meters above the bottom of the track as shown in this figure above, and is released from rest. It slides with negligible friction down the track around the inside of the loop of 0.6 meters and leaves the track at point C, a height 0.5 meters above the bottom of the track. A wants us to calculate the speed of the block when it leaves the track at point C. Well, since the whole track, the whole system is frictionless, this allows us to use point A and point C to do a conservation of energy calculation. At point A, the type of energy is all gravitational potential, therefore the initial mechanical energy is simply mgho. At point C, we're going to use this spot as the base level in my calculation, and therefore the only mechanical energy at point C would be kinetic, so 1/2 mv squared. Notice that the mass cancels, and we have g at 9.81 times. At what height above point C is point A? Well, A is 2 meters from the bottom, C is 0.5 meters from the bottom, so A is 1.5 meters above point C. Equals 1/2 v squared. Do the calculation. Pause the video if you need time to perform the calculation. And the v, the velocity, would be 5.4 meters per second. B wants, on the figure below, draw and label the forces, not components, that act on the block when it is at the top of the loop at point B. I've done mine on the diagram. You, of course, would need to do it on the figure provided in the answers. But at the top we have the weight straight down, but we also have the track pushing against the block, and that of course would also be straight down, and that is the normal force of the track on the block. So your free body diagram would have two forces down at the top of the loop. C, calculate the minimum speed the block can have at B without losing contact with the track. This is a Newton's second law calculation. Sigma F equals ma. Is the block accelerating? The answer is yes, because it's traveling in a circular path here, a vertical circle in this case. So we put the C on our acceleration, denoting centripetal acceleration. The summation, since both are pointed towards the center of the circular path, would be Fn plus mg equals mv squared over r. Now, they want the minimum speed. At this minimum speed, at that moment, the track would not be pushing back on the block with any normal force, so the normal force would be 0. This causes mg, this means mg is the only cause of the centripetal force at that moment. The mass again cancels, and we're looking for, again, for the v value here. So we go ahead and substitute 9.81. Our radius is 0.6. And solve for v. You need to take the square root of 9.81 times 0.6, and you should get 2.4 meters per second. D, calculate the minimum height, h min, above the bottom of the track at which the block can be released and still go around the loop without losing contact with the track. So they want, at what point up here could you still release it and it will still make it around the circular loop? In other words, at what point up here can you let go of it? At what height can you let go of it? And it would have 2.4 meters per second of velocity at point B. This is another conservation of energy solution. And we're comparing this initial spot, wherever it is, to point B. Well, the initial spot would have only gravitational potential, which would be hg, and that minimum height we're looking for. At point B, we're now going to use the bottom here of the loop as the 0 point, the base level for gravitational potential energy. And so at B, it has gravitational potential energy and kinetic. So mgh plus 1/2 mv squared. Notice the mass cancels in each term. We go ahead and sub in. We know that 9.81 times h min equals 9.81 times, since it's the radius of the circular path is 0.6. The diameter of the circle is 1.2, and that is B's height above the base level, plus 1/2 times 2.4 meters per second that we found earlier. Don't forget to square that in your kinetic calculation. Solve for h min, and you should get 1.5 meters to 2 digits. There you have it for 2010 Form B. Next, we have our 2009 Form B. An experiment is performed using the apparatus above. A small disk of mass m1 on a frictionless table is attached to one end of a string. The string passes through a hole in the table and an attached narrow vertical plastic tube. An object of mass m2 is hung at the other end of the string. The student holding the tube makes the disk rotate in a circle of constant radius r, while another student measures the period, capital P. In A, they want us to derive the equation capital P equals 2 pi square root m1r over m2g that relates P and m2. Now, why they want us to do this will become more obvious later on, but our first task is to derive that equation. Our first step, you probably already get by now that the period is related to the mass by the centripetal force. Ignore this stuff over here on the right for right now. We're going to work down the left side here and then switch over to the right side. So we start off with sigma f equals m1 ac. Is m1 accelerating? Yes, traveling in a circular path. What force is causing m1 to stay traveling in a circular path? Well, it's the tension in the string, but the tension is caused by the hanging weight. So m2g is what causes m1 to centripetally accelerate at v squared over r. Obviously, the period is related to the velocity. So m2g equals m1, 2 pi r is the distance, the circumference traveled in one complete revolution, divided by the time it takes to do that, which is the period. They've replaced the traditional symbol for period of capital T with capital P. We have to remember to square that. Divided by r. Okay? Now, we're going to shift back over here to the right. By squaring, we get m2g equals m1. 2 squared is 4. Pi squared, r squared, over p squared, all over r. We have a double fraction that we need to simplify. Multiply both the numerator and the denominator by the reciprocal of the denominator. This gets rid of our denominator all the way down here. This also eliminates the square in the numerator of our original fraction. So m2g equals m1 4 pi squared over times r over p squared. Now, you can see that I've encased this in a blue rectangle. This equation right here is going to come into play in part B. So more later on that in a second. In the meantime, they want this solved for capital P. So we multiply both sides by P squared and divide both sides by M2G. P squared equals M1 4 pi squared R over M2G. In order to solve for P, we take the square root of both sides. So P is now the square root of M1 4 pi squared R over M2G. They want the 2 and the pi pulled out in front of the radical. So the square root of 4 is 2, square root of pi squared is pi. That's how they get 2 pi times the square root M1R over M2G. And there's your derivation. Okay? Now, part B. We flip the page to see a table and a graph. This is the second time you've been exposed to this type of a question. As soon as you see this type of question, hopefully you're starting to learn what they're going to ask you to do here. Let's read the directions first. The procedure is repeated and period P is determined for 4 different values of M2, where M1 is kept constant at 0.012 kilograms and the radius is kept constant at 0.80 meters. The data which are presented below can be used to compute an experimental value for little g. So now they're using this apparatus to uniquely determine the acceleration due to gravity. B. What quantities should be graphed to yield a line with a slope that could be used to determine big G? So from the graph below, they're telling you straight out that they want you to get a linear fit of your data and that you're going to use the line's slope to help determine little g. Notice that it says that could be used to determine little g, not that the slope is little g. All right. So what that means is we need to take some part of the work that we just did in our derivation and get it into y equals mx plus b format. Now, from our past work, a linear fit that shows a direct relationship, you know the y-intercept is going to be nearly or exactly 0. So, how can we manipulate any portion of the work we've done to be in y equals mx plus b format? Remember, they told us the value of m1, pi is a constant, and they're keeping r constant also. So it should pop out to you that this right side up here can be used for your y term, for your y variable. G will be somehow related to the slope, and m2 will become your x variable. You're taking this equation and putting it in y equals mx plus b format. Okay? Notice I've subbed in the constants variables here. So you've got this over p squared equals g, m, times m2, x, plus 0. Now, what does that mean then? What quantities would we have to graph? Our y is going to be 1 over p squared. Our x variable is going to be m2. Now why 1 over p squared? Because we already know the numerical value of all this is 0.3790 by doing the calculation of what this numerator is worth. So this is a constant. This number, 0.3790, is never going to change in this particular part of the experiment. Now, on the grid below, plot the quantities determined in part B, label the axes, and draw the best fit line to the data. You may use the blank rows above to record any values you may need to calculate. So the first thing we're going to recognize in our data table is that they gave us the values of M2 and P. We need the values of M2 and 1 over P squared. So the first thing we're going to do is go through and determine the values of 1 over P squared. So we need to take the inverse of each of these quantities squared in the data table. And you should get, checking your answers, 0.510, 0.907, 1.56, and 1.78. We then take these quantities, label our axes, assign appropriate scales, and graph the data of 1 over P squared and M2. It should be obvious to you that you're not getting a perfect fit, meaning the line is going to pass through every data point. So you draw the best fit line, the best that you can. General rule, we have 2 points above the line, we have 2 points below the line. There's going to be some interpretation by individuals how that line passes through the point, therefore acceptable leeway in our answer at the end. But it should look something similar to this. In part D, they now want us to use your graph to calculate the experimental value of little g. So clearly, we're going to calculate the slope and somehow use that to determine little g. Let's take a look at how we're going to do that. Well, the slope, change in y or change in x, is going to be 1 over P squared over M2. Simplifying this, again, double fraction, multiplying numerator and denominator by reciprocal of denominator, you would end up with 1 over M2 times P squared. I shortcut the algebra there. If you need to pause and work that out for yourself, go ahead and do that. Now, remembering that we have that constant also to take into account, that 0.3790 went above the P squared in the other equation. So 0.3790 over P squared times M2 is equal to little g, using the y equals mx plus b format. So little g is equal to the slope times 0.3790. We go ahead and determine what our slope was. I selected these 2 points which intersected grid pattern on my best fit line. You could use any points at all up through here that do that. Okay, this one would have been close and good points to use also. But for mine, I got a change in y value of 1.0 minus 1.5. These 2 points right here. My change in x, 0.04 minus 0.02 times the constant value of 0.3790. Now, in mine, I got a 9.5 meter per second squared little g value. Using graphing software to find the perfect slope comes out to be 8.8 meters per second squared. Generally speaking, on a question like this, they're going to go plus or minus 1 for acceptable leeway. So your answer probably would need to lie between 7.8 and 9.8 meters per second squared. I would encourage you to pause the video at this time. Make sure that that you've taken the time to understand this question, to do all the calculations, and you're not just copying down what I have here. Next, we have the free response question from 2004. A roller coaster ride at an amusement park lifts a car of mass 700 kilograms to point A at a height of 90 meters above the lowest point on the track as shown above. The car starts from rest at point A, rolls with negligible friction down the incline, and follows the track around a loop of radius 20 meters. Point B at the highest point in the loop is at a height of 50 meters above the lowest point in the track. A1. Indicate on the figure the point P at which the maximum speed of the car obtained. Of course, you would label the bottom of the hill as the fastest at the fastest spot for which the car would be going. Part 2. Calculate the max value V max of this maximum speed. And for that, of course, you would use conservation of energy. So up here at A, just gravitational potential. Down here at P, you would have its maximum kinetic. 9.8 mass cancels. 9.81 times 90 equals 1/2 Vmax squared. Solving for Vmax, you should get 42 meters per second. For B, calculate the speed VB at the car of point B. Again, you're going to conserve mechanical energy. I switched and used point B as the base level. So at A is at a height above B. So it has gravitational potential, and then we have just kinetic at point B. Mass cancels again, and we get 9.81. B is 40 meters below A, 90 minus 50. So the initial height of A above B is 40 meters equals 1/2 VB squared. Solving for VB, and we get 28 meters per second. C wants us to C1 on the figure of the car below. Label vectors to represent the forces acting on the car when it is upside down at point B. And this, of course, would be the weight of the car down and the normal force of the track pushing downward against the car as well. So you have both the weight and the normal force downward. C2 wants to calculate the magnitude of all the forces identified in C1. The weight's pretty straightforward. That's going to be a W equals mg calculation. So 700 times 9.81, and you should get generally 6,860 newtons. Not stressing on sig figs in this question because they were pretty poor about labeling what that was. Based on the information they provided, it would be 1, and we don't ever do that. For the normal force, that's going to require a Newton's second law, recognizing the car is going in a circular path. So it is accelerating with a centripetal acceleration. At point B, the normal force plus the weight causes the car's mass to centripetally accelerate at v squared over r. We already found the weight in in the first part of C2. We know the mass, we know the speed it's going at point B is 28, and we know the radius of the circular path is 20. So we go ahead and sub in all our known values, and we solve for the normal force. The normal force would be 20,580 newtons. D wants us to say, now suppose the friction is not negligible. How could the loop be modified to maintain the same speed at the top of the loop as found in part B? Justify your answer. So, now this track does have friction. If we left B where it was, and with friction, because there's a loss of mechanical energy, the car will not be going as fast at point B as what we calculated here, neglecting friction. However, they want the car to still be going this speed at point B. So follow this. The kinetic at point B needs to remain the same. But we understand there's going to be a loss of mechanical energy. So, in order to keep the kinetic the same at point B, we need to reduce the gravitational potential that B has to compensate for the loss of mechanical energy on the track. So point B would have to be lowered. There will be mechanical energy loss due to friction. In order for the kinetic at B to remain the same, the gravitational potential at B has to be decreased to compensate for the loss. So the height has to be lowered. Next, the free response question from 2001. A ball of mass big M is attached to a string of length big R and negligible mass. The ball moves clockwise in a vertical circle as shown above. When the ball is at point P, the string is horizontal. Point Q is the bottom of the circle, and point Z is the top of the circle. Air resistance is negligible. Express all algebraic answers in terms of the given quantities and fundamental constants. So this is going to be one of those questions with no numbers, and all our answers have to be only in terms of M and R and any fundamental constants, for example, like acceleration due to gravity. In A, they start off with asking for free body diagrams. Draw and label all the forces exerted on the ball when it's at points P and Q. Well, at the bottom of the swing over here, you're going to have the weight down and the tension straight up. Over here at point P, the weight is still straight down, but the tension remains towards the center of the circular path and is therefore to the right. B, derive an expression for Vmin, the minimum speed the ball can have at point Z, which is the top of the circle, without leaving the circular path. Well, the minimum speed, if we were to imagine the free body diagram up here at Z, would be the weight straight down and the tension straight down. But at the minimum speed, the string would become slack, so there's no tension in the string. So our sigma F equals ma, our Newton's second law expression. Ball is accelerating because it's moving in a circular path. As just mentioned, it would be T plus mg, but you don't see T here because the value of the tension is 0. So the weight is the only thing causing the mass to centripetally accelerate. So big mg equals big M v squared over big R, as given in the problem. Solve for v, multiply both sides by big R, and take the square root. So the answer, little v, equals square root of rg. We look at our answer over here on the left. Both of these are allowed, and we're good with our answer. C, the maximum tension the string can have without breaking is T max. Derive an expression for V max, the maximum speed the ball can have at point Q, bottom of the swing, without breaking the string. Well, again, we're doing another Newton's second law. Sigma F equals ma, still accelerating. This time, the summation would be T towards the center of the circle minus big mg, which is away from the center of the circle, equals big M v squared over R. They want this solved for the maximum velocity. Now, they gave us the tension, so we're allowed to have that in our answer. So we multiply both sides by R, so we get big R times the quantity T minus mg equals big M times v squared. Divide both sides by big M and take the square root, and there you have an expression for the max velocity at the bottom of the swing. D, suppose the string breaks at the instant the ball is at point P. Describe the motion of the ball immediately after the string breaks. So the ball comes around. Right here at point P, the string breaks. Remember that the velocity of an object traveling a circular path is tangent to that circular path. So at point P, the velocity would be straight up. So the string breaks at this moment is going to travel straight up, pause, and then fall straight back down. So this ball would move as a one-dimensional projectile straight up because its velocity is tangent to the circular path at that moment. An incorrect answer is to say that at point P that it would travel as a two-dimensional projectile going outward like this. Okay, that shows that the velocity would be at an angle here, but it's not, since the string is horizontal at this spot. Okay, and it breaks at that moment. The velocity would be tangent, which is straight up. Next, the free response question for 1999. A coin C of mass 0.0050 kilograms is placed on a horizontal disc at a distance 0.14 meters from the center, as shown above. The disc rotates at a constant rate in a counterclockwise direction as seen from above. The coin does not slip, and the time it takes for the coin to make one complete revolution around is 1.5 seconds. The figure below shows the disc and coin as viewed from above. Draw and label the vectors on the figure below to show the instantaneous acceleration and linear velocity vectors for the coin when it is at the position shown. This is interesting because typically they ask you for a free body diagram. In this particular case, they ask you for motion vectors. Well, you know for an object traveling in a circular path that its acceleration is centripetal acceleration and is pointed towards the center of the circle. So on the coin you would have an AC pointed to the left. You also know that its linear velocity is tangent to the circular path at that moment. So at this spot you would draw the velocity vector directed straight up and labeled V. And that's your answers for A. B wants the linear speed of the coin. Well, you've been down this path before. V equals x over t. The distance traveled or displacement is the circumference once around the circle, 2 pi r. So in this case 2 pi and the radius is 0.14. And the period of revolution, the amount of time it takes to get all the way around, is 1.5 seconds. Do your calculation and you should have gotten 0.59 meters per second. And C, the rate of rotation of the disc is gradually increased. The coefficient of static friction between the coin and the disc is 0.50. Determine the linear speed at which the coin when it just begins to slip. So here we are at another Newton's second law calculation. Sigma F equals ma. The coin is of course accelerating because it's traveling in a circle. What is the force causing the coin to stay traveling in a circular path? Of course, that force that's causing the mass of the coin to centripetally accelerate is the static friction between the coin and the disc. How do we calculate static friction? You may remember μs normal force. This object is on a flat horizontal surface, so the normal force is equal and opposite to the weight of the coin. So μs mg equals mv squared over r. Notice the mass of the coin cancels. That plays in our answer to D here in a moment. Okay? We want V to be calculated, so we go ahead and substitute. 0.5 times 9.81 equals V squared over 0.14. Go ahead and solve for V, and we get 0.83 meters per second. D, if the experiment in part C were repeated with a second identical coin glued to the top of the first coin, how would this affect the answer to C? Explain your reasoning. Well, the answer is that would have no effect. And the reason, of course, is because mass cancels. The speed is independent of the mass since the mass cancels. Mass has nothing to do with calculating the speed. Next, the free response question for 1997. To study circular motion, 2 students used the handheld device shown, which consists of a rod on which a spring scale is attached. A polished glass tube attached at the top serves as a guide for a light cord attached to the spring scale. A ball of mass 0.2 kilograms is attached to the other end of the cord. One student swings the ball around at constant speed in a horizontal circle with a radius of 0.5 meters. Assume friction and air resistance are negligible. Ignore these force labels here. That's for a question that's down in part E, and we'll come back to that in a few moments. A, explain how the students, by using a timer and the information given above, can determine the speed of the ball as it's revolving. You're going to be using an apparatus very similar to this in the lab setting. It's not identical because you're not going to be using a spring scale, but very similar to this in order to do the lab. How is the velocity determined? Well, the velocity is distance divided by time, and once again, the distance is the circumference of the circular path, and the time is the period of revolution. The circumference is given by 2 pi r, and the radius is given. So by using the stopwatch, by using the timer, you can determine the period and then divide, and you can get the velocity. B, how much work is done by the cord in 1 revolution? First of all, why is the cord doing the work? And that's because the tension is keeping it traveling in a circular path. So how much work is that force doing in 1 revolution? The answer, of course, is 0 joules. And the reason it's 0 joules is because the displacement in 1 revolution is also 0. Work is force times displacement. If the displacement is 0, then the work is 0. C, the speed of the ball is determined to be 3.7 meters per second. Assuming the cord is horizontal as it swings, calculate the expected tension in the cord. As just mentioned, when we do our Newton's second law summation, sigma F equals ma, the ball is accelerating because it's traveling in a circle, so it's centripetally accelerating. The only force causing it to stay in the circle is the tension in the cord. So T equals mv squared over r. We know the mass is 0.2. They gave you the speed is 3.7. Don't forget to square it, and the radius of the circular path is 0.5. So the tension is given to be 5.48 newtons. They did a good job in this question of all your data being to 3 digits. So your answer here should be to 3 digits. In part D, the actual tension in the cord as measured in the spring scale is found to be 5.8 newtons. What is the percent difference between this measured value of the tension and the value calculated in part C? Well, why are we doing a percent difference calculation? Percent error calculations are done when we have an accepted value for the experiment, such as experiments when we've calculated acceleration due to gravity. We know the accepted value is 9.81, so we do a percent error calculation because we have an accepted value. In this particular experiment, we do not have an accepted value for the tension in the string. So to do that error analysis, we do what is called a percent difference calculation. In that calculation, we do a calculated value minus a measured value, and it's the absolute value, so we don't have to worry about whether that numerator is positive or negative. So the calculated minus the measured, here's the difference, divided by the average of the 2 values. We take the average of the calculated and measured value, and then we multiply that by 100% to get our percent difference. So this is what we do when we don't have an accepted value, which we would put in the denominator here. In this case, we do the average of the 2 values. So our percent difference, we have a calculated value of 5.8. I'm sorry, we have, again, it doesn't matter here. You can reverse it any way around here. You can do an absolute value anyways. But the measured value was 5.8. The calculated value is 5.48. Subtract them and divide by the average of those 2 values, and you should get 5.7%. Okay. All right. E wants the student finds that despite their best efforts, they cannot swing the ball so that the cord remains exactly horizontal. On the picture of the ball below, draw vectors to represent the forces acting on the ball and identify the force that each vector represents. I'm going to scroll back up here to the diagram that I have. We're going to use the ball as located in the picture. Well, what forces would be acting on the ball? Well, you have the weight straight down, and you have the tension at a slight angle upward from the horizontal. The two red forces drawn here in this diagram would be the forces on your free body diagram for part E1. Part E2, explain why it is not possible for the ball to swing so the cord remains exactly horizontal. I've added two components here to this diagram in blue. We have the Y component of the tension upward and the X component of the tension to the left. It should be noted that the X component of the tension to the left is what's causing the centripetal force, keeping the ball traveling in a circle. What's Ty doing? If you look at the diagram, the vertical component of the tension is supporting the weight of the ball. Follow the logic here. The ball will always have weight. That means there will always be vertical component of tension to support that weight. Well, there's always a Ty value. That means there will always be a right triangle formed by T, Ty, and Tx. If there's always Ty, therefore the opposite leg, there will always be an angle at which this tension is produced. So it's ultimately because the ball has weight. Therefore, a vertical component of tension is required to support that weight, and because there's a vertical component of tension, there will always be an angle, even if it's small, for that tension to be directed slightly upward. And part 3, calculate the angle that the cord makes with the horizontal. Well, what trig function relates Ty, the tension itself, and the angle at which the ball is swinging around in a horizontal circle? That, of course, would be sine. Ty would be over here, opposite the angle, and T is the hypotenuse. So we know that Ty is equal and opposite to mg, so that's our shortest way to figure out the answer. So summating forces in the y direction. In the y direction, the ball is not accelerating. So the upward T sine theta equals the downward mg. Substitute, and we've got theta to be the inverse sine of mg over t, and that would be the inverse sine of 0.2 times 9.81 over 5.8, and we are using the actual tension recorded in the spring scale for that, and that gives you an angle, an upward angle of 20 degrees. Next, the free response question for 1995. Part of the track of an amusement park roller coaster is shaped as shown as above. A safety bar is orientated lengthwise along the top of each car. In one roller coaster car, a small 0.1 kilogram ball is suspended from this bar by a short length of light and extensible string. A. Initially the car is at rest at point A. On the diagram to the right, draw and label all the forces acting on the 0.1 kilogram ball. And that would be the tension upward on the ball and the ball's weight downward. Okay? So these would be the forces that you would include in your free body diagram on the diagram provided in the answer book. And then A2, calculate the tension in the string. Well, this is at rest, not accelerating in any direction. So vertically, the tension, upward tension, has to be equal to the downward weight. The tension is 0.10 times 9.81 to 2 digits. Since they've done a nice job of emphasizing that to 2 digits here, our tension would be 0.98 newtons. Next, the car is then accelerated horizontally, goes up the 30-degree incline, goes down a 30-degree incline, and then goes around a vertical circular loop of radius 25 meters. For each of the 4 situations described in parts B to E, do all 3 of the following. In each situation, assume that the ball has stopped swinging back and forth. They want us to first determine the horizontal component TH of the tension in the string in newtons and record your answer in the space. 2. Determine the vertical component TV of the tension in the string in newtons, record your answer in the space. And 3. Show on the adjacent diagram the approximate direction of the string with respect to the vertical. The dashed line shows the vertical in each situation. What I would say to you, the best approach here is that we're going to do the 3rd bullet first. We're going to label the diagram, because by labeling a diagram, it will help us understand and how to calculate the 2 components of the tension. So, in B, the car is moving at point B horizontally to the right with an acceleration of 5 meters per second squared. So what would the ball be doing if it was accelerating to the right? I think intuitively we all understand that the ball would swing back. So we just draw the string with the ball attached to it back behind the vertical dashed line here. For the horizontal tension, we summate forces in the x direction equals ma. Is the ball accelerating horizontally? We see here in the diagram that it is. So TH, the only force acting on the ball, horizontal component of tension, equals 0.1 times 5. So TH would be 0.50 newtons. In the vertical direction, the ball is not accelerating. So we're back to the same scenario as up here. The vertical component is equal to the weight, which we calculated earlier to be 0.98 newtons. Off to a good start so far. C, the car is at point C, is being pulled up the 30-degree incline with constant speed of 30 meters per second. Well, if it's moving at constant speed, that means the ball is just going to be hanging straight down because it's not accelerating. So if it's hanging straight down, there is no horizontal component of tension, so that's 0. And the vertical component of the tension will be equal to the weight, 0.98 newtons. D is the tricky one. The car is at point D, moving down the 30-degree incline with an acceleration of 5 meters per second squared. So what would happen here? Well, relative to the vertical, we again intuitively understand that the ball would swing backwards. So we draw our string with the ball hanging back behind the vertical dashed line here. Now the reason this is tricky is because the acceleration is directed along the line of the track here. But there's a component of this acceleration that's horizontal, and there's a component downward of this acceleration that is vertical. So sigma f in the x direction equals ma. Is the ball accelerating horizontally? Yes, with this horizontal component of the acceleration, and that would be a cosine theta. So th is the mass, 0.1 times 5 cosine of 30 degrees. We get a horizontal component of 0.43 newtons. We summate forces in the y direction equals ma. Is the ball accelerating vertically? Answer, yes, it has this vertical component of acceleration, which would be a sine theta. However, what would be the summation? Since this acceleration is downward, we follow our rules that the direction of motion is deemed positive. So on our free body diagram, you can see the weight is downward, the vertical component is upward of tension. So it would be mg minus TV equals ma sine theta. We know the weight's 0.98. We're solving for TV, 0.1 times 5 sine 30. Solve this for the vertical component of tension to be 0.73 newtons. E, the car is moving at point E upside down with an instantaneous speed of 25 meters per second and no tangential acceleration at the top of the vertical loop of radius 25 meters. Here's where we're going to apply our circular motion concepts. But first, let's take a look at the diagram. The ball would be pointed straight up. Okay, upside down, attached to the roof of the car, the ball would be pointed straight up. This makes the horizontal component of tension easy because there is none, so it would be 0. For the vertical component, we summate forces in the y direction. Is the ball accelerating? Yes, traveling in a circular path. What would be the summation? Well, the tension here is directed downward, and so is its weight. So TV plus mg equals mv squared over r. We go ahead and we substitute, and we calculate the vertical component of tension to be 1.5 newtons. Lastly, the free response question from 1992. A 0.10 kilogram solid rubber ball is attached to the end of an 0.8 meter length of light thread. The ball is swung in a vertical circle as shown in the diagram above. Point P is the lowest point in the circle, is 0.2 meters above the floor. The speed of the ball at the top of the circle is 6 meters per second, and the total energy of the ball is kept constant. A. Determine the total energy of the ball using the floor as a 0 point for gravitational potential energy. Well, we understand that the total energy is the sum of the kinetic and potential energy. The only spot where we're able to calculate the total energy at the moment is at the top. Because we know the speed, therefore we are able to calculate the kinetic, and we're able to find the height above the floor, so we're able to know the gravitational potential. Adding those two together will give us the total energy of the ball at that spot. So the total energy is the kinetic possessed at the top plus the gravitational potential at the top. 1/2 0.1 times 6 squared plus 0.1 times 9.81. And the circle has a diameter of 1.6, twice the radius, and it's 0.2 meters above the floor. So the total height at this top of the circle is 1.8 meters. Go ahead and do your calculation and you should get 3.6 joules. B wants the speed of the ball at the lowest point P at the bottom of the circle. Well, we know the total energy is 3.6 joules and we're told that it's kept constant. Here we know the height of P above the floor, so we know and are able to calculate the gravitational potential. We're able to apply conservation of energy again to then determine the speed. So the total energy of 3.6 joules is equal to 1/2 0.1 V squared plus 0.1 times 9.81 times 0.2, the height above the floor. Solving for V, we should get 8.3 meters per second. C wants the tension in the thread at the top of the circle and the bottom of the circle. At the top of the circle, our forces are going to be the weight down and the tension down. So, when we do a sigma F equals ma, yes, the ball is accelerating, we add the forces at the top of the circle. Both are directed towards the center of the circular path. So T plus mg equals mv squared over r. Go ahead and do our substitutions. 0.1 times 9.81 equals 0.16 squared over 0.8. Do this, subtract this value, and you should get a tension of 3.5 newtons. At the bottom of the circle, the tension would be up while the weight is down. Tension being directed towards the center of the circle makes it positive, and the weight opposite that makes it negative. So at the bottom of the circle, T minus mg equals mv squared over r. We substitute in. This time we add the weight to the other side using the appropriate numbers for substitution here, and we get 9.6 newtons of tension at the bottom of the swing. That should make sense that there's greater tension at the bottom than there is at the top. Next, we're told the ball only reaches the top of the circle once before the thread breaks when the ball is at the lowest point of the circle. Determine the horizontal distance that the ball travels before hitting the floor. Okay, so this thing is coming around here, only goes once, gets to the bottom, and the string breaks at this moment. Well, yes, velocity is tangent to the circular path, but how will the ball move? It will travel as a horizontal projectile and then hit the floor. They want the horizontal distance that the ball travels before hitting the floor. This is your traditional projectile motion calculation, in which you're using the vertical motion to find the time and then the horizontal motion to find the range. For the vertical motion, we have the height to be 0.2 above the floor. There is no initial velocity vertically, so that value is 0, plus 1/2 gt squared. 1/2 0.2 equals 1/2 9.81 times t squared. Solve for t, taking the square root, and you get 0.20 seconds. You know the velocity at the bottom of the swing is 8.3 meters per second, equals the range over that time, 0.20 seconds. Multiply the two, and you get a horizontal distance, the range, to be 1.7 meters.